Welcome to Spring LIB.
Okay, so we're doing chapter 23, problem 53. So it wants us to use the results from some older problems to determine the electric field due to the uniformly charged rod of figure 31. Okay, and for part A, it says along the y-axis, and part B wants us to do along the x-axis. Okay, so if we look at the answer from problem 38, it tells us that the potential along the y-axis is given by Q over 8 pi epsilon naught L, and then the natural log of square root of L squared plus y squared plus L minus the natural log of the square root of L squared plus y squared and then minus L. Okay, so if that's our Vy on the y-axis, if we're trying to figure out what the electric field is, we should know from just a symmetry argument that the field will only point along the y-axis. So that means E equals Ey times J. So let's figure what that is. So Ey is given as negative partial V partial Y. So we can just, since we have the expression for Y or V, we can just differentiate. So let's do that. So from the beginning, we know that we're going to have our constants here, Q over 8 pi epsilon naught L. And now we got to differentiate the inside. So first we should see this comes out to being 1/2 L squared plus y squared and negative 1/2 all times 2y. This is all over y squared plus L squared plus L. Okay. The second part's going to be almost identical, just with a minus L on the bottom. So let's write this out. Times 2y all over y squared plus L squared minus L. And now we forgot our minus sign from here, so let's add that in. Cool. So let's start simplifying. We have minus q over 4 pi epsilon naught L. Sorry, that's 8 pi. That's why it looked weird. Okay, so 8 pi. Now we have a square root of L squared plus y squared times y over L squared plus y squared plus L minus y L squared plus y squared over L squared plus y squared minus L. And if we combine like terms and actually subtract these off, this actually simplifies very nicely for us, surprisingly. And we're left with q over 4 pi epsilon naught y square root of L squared plus x squared. Sorry, y squared. I don't know why that was next. Cool. So that's Ey. So that means for part A, we know that the vector quantity E, since our symmetry argument is just given as Q over 4 pi epsilon naught y, and then square root of L squared plus y squared, all in the j hat direction. Cool. So this was kind of a hard differential problem, but we got there. Let's do part B now. So for part B, they found V along the x-axis, and this was given by Q over 8 pi epsilon naught L, something kind of similar, ln of x plus L minus ln of x minus L. So from the same argument as before, we should know that the electric field then is going to be pointing only in the x-axis here by the symmetry argument. So that means this is just Ex times I hat. And EX is given as the negative partial v partial x. So let's just differentiate. We have negative q over 8 pi epsilon naught L. Differential of x over ln of x plus L is just 1 over x plus L. And then x minus L is that. Cool. Let's now combine like terms, and this becomes 1 over 4 pi epsilon naught q over x squared minus L squared. Awesome. This one was a lot easier. So that's our EX. So let's go ahead and write this out in vector quantity. And that is q over 4 pi epsilon naught and 1 over x squared plus L squared, all in the I hat direction. Kind of small here, but that is the answer. Sweet.